Hi everybody, I'm Ray Li, a PhD student from Shandong University. It's my pleasure to introduce our work on Android security. It's a joint work with Wenrui Diao, Zhou Li, Jianqi Du, and Shanqing Guo. The topic is about Android custom permissions. Okay, let's start. Permission is a fundamental security mechanism for protecting user data and privacy on Android. There are two kinds of permissions. One is a well-known system permission provided by the OS to protect system resources. The other is a custom permissions declared by the third-party app to protect its own resources. There are lots of previous research focused on the security of Android permission mechanism. However, most of them focus on system permissions. The security implications of using custom permissions have not been fully understood. In our work, we systematically study the security of custom permissions. We first conducted a large-scale measurement to understand the status quo of using custom permissions. The results show that about 25% of apps declare custom permissions. We could find that the use of custom permission is common. In Android, permissions are mainly divided into three protection levels. Normal and signature permissions are granted when installing an app. Thus, they are also called install time permissions. On the other hand, the user can choose to grant or deny dangerous permission at runtime. Therefore, dangerous permissions are also called runtime permissions. Permissions are organized into groups related to a device's capabilities or features. All dangerous permissions belong to permission groups, and any permission can be assigned to a group regardless of protection level. Also, dangerous permissions are granted on a group basis. If an app has been granted a dangerous permission, it can get all the other permissions belonging to the same group without user interaction. In order to enforce a custom permission, the app must first define it in its manifest file using the permission element. Let's see this example. This is a normal level custom permission. The permission name is unique. If the name is the same as an existing permission, this custom permission will be ignored by the system. Besides, the normal permission is granted automatically. This custom permission is assigned to the storage group, and this behavior is optional. To use this custom permission, the app needs to request it through the uses permission element. The previous work ever discovered custom permission-based privilege upgrade attack. In this permission upgrade attack, the adversary can get the dangerous permission without user consent. In Android 10, this issue has been fixed. However, through adding the extra app installation operations, we can still achieve the same privilege escalation. This preliminary exploration motivates us to think about how to check the security of the communicated permission mechanism effectively. The previously fixed bug may be only the tip of the iceberg, and an automatic analysis tool is needed. Inspired by the motivation case, we abstract the analysis process as finding specific app execution sequences that can trigger privilege escalation issues. Accordingly, the internal operations of the permission mechanism can be treated as a black box. Besides, our target is to identify the shortcomings lying in the permission framework, not just discovering successful attack cases. The adversary can exploit the shortcomings to access unauthorized platform resources, such as getting dangerous system permissions without user consent. Following the high-level idea, we designed an automatic filing tool, CubeFather. It tries to trigger privilege escalation issues by executing massive test cases. As mentioned before, each test case is essentially an app execution sequence composed of various test apps and permission-related operations. After reviewing the Android technical documents and source code, we confirmed three operations: app installation, app uninstallation, and OS update. All of them can trigger the system to refresh the granting status of permissions. As described in the picture, Kuberfather contains 5 main steps. It first generates a tester app as a seed to activate the subsequent fathering process. Next, it constructs plenty of complete cases for testing. Then, it executes tester keys on multiple physical phones in parallel. After executing a tester case, it checks whether this case is an effective case based on the predefined rules. Finally, among discovered defective cases, it filters duplicated cases and identifies critical paths to facilitate notating the causes. We implemented Kuberfather. Expressly, we deployed a laptop and 4 Google Pixel 2 phones to achieve parallel execution. Our experiments focus on the security of Android 10 in order to solve some issues that need manual interventions, such as ADB authorization and unlocking the screen. We also compared 2 versions of Android OS images based on the source code of Android 9 and 10. During our experiment, Kuberfather executed more than 40,000 tester cases. Finally, it discovered more than 2,000 effective cases and further got 30 critical paths. We manually analyzed these critical paths and identified these 4 design shortcomings. Following the responsible disclosure policy, we reported these flaws to the Android security team, and all of them are rated as high severity and assigned CVD IDs. Currently, all flaws have been fixed. Due to the time reason, here we only illustrate design shortcoming number 2 as a showcase in detail. Design shortcoming number 2 is inconsistent permission group mapping. As mentioned before, the grant of dangerous permissions is group-based. When processing a dangerous permission granting request, the system will query the requested permissions group information. However, we found that system and custom permissions rely on different forces to obtain the permission group mapping relationship. For system permissions, the group information is obtained from the platform permissions. In platform permissions, system permissions belong to the corresponding system groups. For custom permissions, the system will invoke package manager to get the group information from the file Android manifest. However, in Android manifest, all dangerous system permissions belong to the undefined group. Exploiting such inconsistency, an adversary can get all dangerous system permissions without user consent. Let's see the attack case. The adversary creates an app test, which requests the right external storage permission. She also prepares an updated version of the app test, which defines the dangerous custom permission and puts it into the undefined group. It also requests this custom permission and all dangerous system permissions. The user first installs the app test and grants the right external storage permission to it. Then she updates test. Next, when the system processes a custom permission granting request, all dangerous system permissions will be mapped to the undefined group incorrectly. And since the app has been granted with the right external storage permission of the undefined group, it will get all dangerous system permissions without user consent. Let's see the real attack demo. We install the app PG tester first. The installation starts. It's a little bit slow. Okay, the installation is done. We check the permission granting list of this app. We can see that at this time, this app has not been granted any dangerous system permission. Now, we grant it a storage permission. We check the permission granting list again. We can see that this app has got a storage permission. Then, we'll install the updated version of this app. We confirm the installation. Okay, the update is done. We check the permission granting list. We can see that this app still only gets a storage permission. Now, we request the dangerous system permissions. We check the permission granting list. We can see that this app has got all dangerous system permissions automatically. This app has achieved privilege escalation. Okay, let's take a quick look at the other three shortcomings. Shortcoming number 1 is juggling custom permission. We found that if an install time custom permission is removed during the app installation or update, the corresponding granting status of apps will be kept. Exploiting this shortcoming through app installation and uninstallation operations, an adversary can get the arbitrary dangerous system permission without user consent. Shortcoming number 3 is custom permission elevating. We found that when Android OS changed the custom permissions owner to the system during the OS initialization, the granting status of this custom permission will not be revoked. This shortcoming is introduced when Google fixed the pile-up flaw found by the previous research. Exploiting this shortcoming through app installation and OS update operations, an adversary can get a new dangerous system permission added in Android 10 without user consent. Shortcoming number 4 is inconsistent permission definition. We said that during the app update, the permission definition held by the system is different from that of the owner app. This shortcoming is introduced when Google fixed the permission upgrade tag mentioned before. Yes, again, fix one issue and introduce new one. Google is always careless. Exploiting this shortcoming through app installation and device reboot operations, an adversary can get an arbitrary dangerous system permission without user consent. After analyzing these flaws to secure custom permissions, we propose two general guidelines. The first one is that if the definition of a permission is changed, the corresponding grants for apps should be revoked. This guideline can cover shortcoming number 1, 3, and 4. The second is that the definition of a permission held by the system should be consistent with the permission owner's declaration. This guideline can cover shortcoming number 2 and 4. At the end, let's briefly summarize our work. We systematically studied the security of Android custom permissions. We designed CubeFather, a black box father, to detect custom permission-related issues automatically. Using this tool, we found 4 fundamental shortcomings lying in the permission framework. We also proposed 2 general design guidelines to avoid similar flaws. If you are interested in our work, you can go to the website to watch more demos. Thanks.